Hello everyone. Let's learn about the diffraction and interference of mechanical waves today. This lecture mainly includes 5 points. 1. The principle of Wiggins. 2. The diffraction of waves. 3. The superposition of waves. 4. The interference of waves. 5. The standing wave. Through the learning of this course, I hope to achieve the following teaching objectives. 1. Master the connotation of Wiggins' principle. 2. Learn to use Wiggins' principle to explain the diffraction and interference of waves. 3. Be able to use the knowledge to explain the diffraction and interference phenomena in life. 4. Be familiar with the application of diffraction and interference in ultrasonic testing and explain it. First, let's look at Wiggins' principle. The Wiggins principle means that every point that the wave reaches can be regarded as the wave source of the wavelet, and at any time after that, the envelope of the wavefront of these wavelets determines the new wavefront. The wavefront here refers to the spatial shape composed of particles with the same vibration state in the median at a certain moment.
The envelope trace is also called envelope line.
From the figure, according to the description of Wiggins' principle, we can infer the wavefront at time t plus capital delta t from the wavefront at any time t, and then determine the direction of wave propagation. Please look at figure 1. At time point t, the wavefront is spherical, and each particle on the surface acts as a wavelet source to generate its small spherical wave.
After a period of delta t, what is the shape of the wavefront where the wave reaches?
It is the wave envelope of those small spherical waves, and it is also a numerical wavefront. In this way, we can also apply it to the analysis of plane waves as shown in figure 2. What is the significance of Wiggins' principle? Please focus on the diffraction of waves. Diffraction of a wave refers to the phenomenon that when a wave encounters an obstacle, it continues to propagate around the edge of the obstacle as the picture shows. The wave also appears on the back of the obstacle due to the diffraction of the wave. Then we illustrate the characteristics of diffraction through some figures here. There are 2 obstacles, one large and one small. On the propagation path of the wave, the diffracted waves appear behind the obstacles. Please observe carefully. The size of the obstacle in the first picture is larger than the wavelength, and the diffraction of the wave is weak. On the other hand, in the second image, the size of the obstacle is smaller and the diffraction of the wave is stronger. Usually, 1. When the size of the obstacle is greater than 10,000 times the wavelength, the diffraction of the wave is not obvious and mainly behaves as a straight line propagation. Diffraction of waves is significant when the obstacle size is less than 1,000 times the wavelength. In other words, long wavelength waves are less susceptible to obstacles. On December the 25th, 2021, NASA launched the James Webb Space Telescope. Its operating frequency range is in the infrared band, which takes advantage of the longer wavelengths of infrared to better avoid the effects of dust in space. The radio signals received by FAST, the world's largest aperture radio telescope, which is independently developed by my country, are also long-wavelength electromagnetic wave signals that can pass through the atmosphere. The sensitivity of FAST is more than 2.5 times that the world's second largest signal aperture radio telescope, and the observation capability is increased by 10 times. It will maintain its world-class status in the next 20 to 30 years. However, in the pulse reflection ultrasonic inspection, if the defect is too small, it may be because the ultrasonic diffraction is too strong, resulting in very few reflected waves, so it is difficult for the probe to receive the reflected signal, and the defect cannot be detected as shown in the figure. In theory, the limit minimum defect of ultrasonic inspection is half wavelength. In ultrasonic inspection, in order to improve the accuracy of a defect location, we should reduce the wavelength, that is, increase the frequency of ultrasonic waves. Now, let's look at the third point, the superposition of waves. When several waves meet, they can keep their respective characteristics and continue to propagate according to their original propagation directions without affecting each other, indicating that the waves are independent. However, in the area where several waves meet, the medium particle is simultaneously subjected to the force of several waves, so its displacement, velocity, and acceleration should be equal to the vectors of displacement, velocity, and acceleration caused by the several waves propagating alone. That is to say, in the meeting area of several waves, the waves will be superimposed, which is principle of superposition of waves. It can also be said that any complex wave can be regarded as a superposition of a series of simple harmonics. After superposition, the vibration of the particle may be strengthened or weakened depending on the result of combination of forces exerted by several waves. By controlling some characteristics of the wave, the vibration of some particles in the superimposed area can also be strengthened, and the vibration of other particles can also be weakened, and the effect shown in the figure. For details, please move to the next point, wave interference. Let us take the encounter of two strings of plane waves as an example. Let their wave equations be y1 is equal to a1 cosine, open parenthesis, omega t plus phi 1 minus kry close parenthesis. y2
is equal to A2 cosine, open parenthesis, omega t plus phi 2 minus kr2, close parenthesis. The propagation mode is shown in the figure.
And they meet at point P.
The synthesized wave equation is y is equal to y1 plus y2 is equal to A cosine, open parenthesis, omega t plus phi, close parenthesis.
According to the parallelogram rule of vector synthesis, the synthesized amplitude A is
capital superscript 2 is equal to capital A superscript 2 subscript 1 plus superscript 2 subscript 2 plus 2 capital A subscript 1 capital A subscript 2 cosine capital delta phi.
the phase inference is
Capital delta phi is equal to phi subscript 1 plus phi subscript 2 minus k, open parenthesis, r subscript 1 minus r subscript 2, close parenthesis.
in the formula, k is the wave number, which is equal to 2 pi slash wavelength. It can be seen that when the phase difference is equal to 0, 2 pi, 4 pi, etc., the
Cosine
value is equal to 1 and the combined amplitude reaches the maximum A1 plus A2. When the phase difference is equal to pi, 3 pi, 5 pi, etc., the
cosine
value is equal to minus 1 and the combined amplitude reaches the minus A1 minus A2. When the initial phases of the two waves are equal, the phase difference depends only on the distance difference between the encounter point and the wave source. Therefore, there must be a stable interference effect in which the vibration of some particles is always strengthened, and the vibration of the other particles is always weakened. Now we can obtain the conditions of interference, the same frequency, and the same vibration direction, and constant phase difference, that is, the coherence conditions. If the amplitude of the particle that is always weakened is 0, the synthesized wave is called a standing wave. What are the conditions for standing waves? Looking at the analysis below. Assuming that there are two columns which are the same amplitude, the same frequency, and the same vibration direction of traveling waves propagation in opposite directions.
The wave equations of the two waves are y1 is equal to A cosine, open parenthesis, omega t minus kx, close parenthesis. y2 is equal to A cosine, open parenthesis, omega t plus kx, close parenthesis.
The wave equation after superposition is
y is equal to y subscript 1 plus subscript 2 is equal to capital A cosine kx cosine omega t. It can be seen that when cosine kx is equal to plus minus 1, the synthetic amplitude reaches the maximum value 2a. These locations are called wave loop. Kx is equal to n pi, open parenthesis, n is an integer, k is equal to pi is divided by lambda, is wave number, close parenthesis. When cosine kx is equal to 0, the synthetic amplitude reaches the maximum value 0. These locations are called wave node. Kx is equal to n, open parenthesis, 2, n plus 1, close parenthesis, pi is divided by 2.
As shown in the animation, this kind of wave gives us the impression that the wave does not propagate forward, so it is called a standing wave. On the contrary, we call the wave that clearly shows the forward propagation of the wave as the traveling wave. Using the principle of standing waves, we can make an interesting experiment. On the metal plate, randomly sprinkle raised grains and makes it vibrate by a vibrator. Adjusting the vibration frequency of the metal plate while pressing different positions of the metal plate by hand will be standing waves of different shapes in the metal plate. Since the rice grains at the antinode vibrate the most, the rice grains at the node are always stationary. So, the rice grains at the antinode will naturally follow to the node, so these rice grains are arranged in different stable patterns. When designing an ultrasonic probe, in order to form a standing wave in the wafer thickness is usually designed to be half a wavelength, and the center of the wafer is at the antinode position to obtain the strongest ultrasonic waves in the center. Through the study, I believe that you have a basic understanding of the diffraction and interference of waves. I hope that you can use them flexibly in the future study of ultrasonic testing. If you are interested in it, you can search the internet for more information of the diffraction and interference of waves. You will find many interesting phenomena. That's all for today. Thanks for your watching.